Nice to be here. It's the first time in LA. A lot of traffic. Good. So everybody can hear me, right? It's fine. Good. Yeah, so I'll try to give a gentle overview of what are the results that we know in learning quantum states. I cannot do an exhaustive survey, but I'll try to do some interesting results which I like, and maybe you get something out of it for everybody. Good. So, right, so what's the overview? So the general question is rho is an unknown quantum state, and I'm going to be looking at a few certain models of learning, and I'll just like right on start, like no motivation, because we all know what's quantum, what's machine learning, and we have hyped it for the past 3 days. So, so we have rho, and the first thing is tomography. You're given copies of rho, learn rho. I'll describe all these models in a bit. Tomography is too expensive, and it's also like you want too much out of the learning algorithm. So let's just say you want to learn approximately well. There's this packed model of learning. There's shadow tomography, which I'll talk about. And then these two things are time inefficient, and then I will talk about Gibbs states of local Hamiltonians, learning stabilizer states. I'll just briefly touch upon it. Daniel will give the next talk on it. And I'll talk of the recent work that we had with Wojta and Luik. I'll just give a brief overview of what we did there, but they will give a detailed talk tomorrow. Good. Let me begin. So tomography. So what is tomography? So rho is an n-qubit quantum state. That means it's a matrix of it's a d by d matrix where d is 2 to the n. It's a PSD matrix. And tomography is you're given copies of rho. And given copies of rho, the goal is to learn rho well enough. By which I mean I just give you copies of rho. You need to output a sigma, such that sigma and rho are close in trace distance. More pictorially, like you have a quantum algorithm here. It's just given rho, tensor rho, tensor rho. Like you give a t-fold tensor copy. And you need to output a state sigma, such that sigma is close to rho. And there are different notions of closeness here, but you could look at trace norm, Frobenius norm, any norm of your choice. And depending on the norm you choose, you'll get different complexities. Right, this is a very fundamental problem. I'm not going to motivate it much more than that. Like, I mean, this is just like, for example, you have an IPAM quantum computer, we spit out a quantum state, like you want to verify, like, this is the state I would have liked to prepare in the first place. So I just given copies of the quantum state, how do I learn it? Of course, there is noise and things like that. I'm not going to get into it for the time being, but just assuming I'm giving pristine copies of rho, I give you copies of this, how many copies suffice to learn rho?
Sorry, Srini, just to confirm, here you've got like the tensor product of all the rows.
Correct.
This seems to me like a special case where you could just be given rows individually and you don't have the space to put them into a tensor product. Like, are you only considering this tensor product case?
I mean, you're given rho tensor. Like, if I give you rho and then I give you another rho, you can view it as a tensor copy.
He's asking if you can use entangled measurement.
This is what I'm asking about.
Oh, exactly. yeah. Okay. That's a good question. Maybe I'll mention it at the end of the slide. Yeah, that's a good question. Yeah, for now, I'm assuming that, let's just say for now, I'm just giving you rho tensor T. What the algorithm can do, I'll just mention it in a second. Although I didn't plan to go into it, but I can mention about that. Right, so there's a trivial algorithm to estimate rho in a trace distance, and the algorithm kind of is like, so rho is a d by d matrix, so there are d square entries you need to estimate well enough. Just estimate every entry well enough, and so estimating each entry, say up to error 1 over d, that takes 1 over d square many copies of rho, and then estimate d square many entries altogether, and the total complexity is like d to the 4. I call this trivial, but there's a little bit of analysis one needs to do to get the d to the 4 upper bound, but this is the trivial algorithm. And then there were, before we get here, so there were a couple of works based on compressive sensing, some theory using some fancy matrix analysis theory where they got this to d cube. And this was, I think, in 2012, but given this is so fundamental, we just didn't know what the right answer was. And there was a breakthrough work in 2015 where they showed the right answer for tomography was d square. And this is kind of like intuitive because the d square entries you need to learn, and you would expect that the sample complexity is d square, but somehow we just didn't know how to prove this for a very long time. And these two breakthrough works of O'Donnell and Wright and Ha et al., they showed the upper bound of d square. And this is known to be optimal.
But this means you have to do like joint measurements on the...
I was going to mention.
Right?
Exactly.
Whereas the first one is like individual.
Exactly. So that's right. So the point is this d square upper bound assumes that you're going to make a giant entangled measurement on this d square fold product state. But if you want to do single copy measurements, this upper bound the upper one that I just mentioned between d cube that they had, that was single copy measurements. And we know that is optimal. That was also proven recently that if you just allow single copy measurements, d cube is the right answer. If you allow a giant entangled measurement, d square is the right answer.
But I mean, also the compressed sensing result improves on the d to the power 4, right? It's also individual copies.
Yeah, it's d cube, right?
Yeah, I think yes.
Yeah, so I think the d cube is for single copy measurements. I think it's based on compressive sensing. Maybe you're on the paper, I'm not sure. Yeah. So the d cube single copy measurement, that's optimal. And if you allow giant entangled measurement, d square is the right answer. And right. I was going to mention a proof sketch of this, but I thought maybe I'll just mention more things than just like bore you with technical details. So like this is all I'm going to say about tomography. If you allow single copy measurements, d cube is the right answer. If you allow entangled measurements, d square is the right answer. But still like d square is like for example, like d is like 2 to the n. So if you have like a 10 qubit quantum state, like you expect like 2 to the 10 copies of an unknown quantum state, and this is just too expensive. And although this is too expensive, there is at least an experimental paper that shows that you can do, I think they did tomography for n equals to 10, but I'm not sure how it worked. But we have one experimental paper that shows that you can do tomography for 10 qubits. Yeah.
I should know this, but I'm just suddenly confused. Is a measurement an evaluation of an expectation value or a shot? It's relevant.
It's a shot.
Yeah.
It's a shot.
Honestly, a shot. Okay.
Yeah.
So that's strange. Quantum computing state. Yeah. Okay.
Yeah.
Because you need much fewer expectation values to discount.
Exactly. Exactly. Good. So like right. So the complexity d square is nice to like theoretically understand what's really going on here, but maybe you can say this is too expensive, and d square is the optimal answer. So d square seems too expensive. Like 2 to the 10 is already expensive for doing tomography on 10 qubits. So motivated by this kind of, I think there was this model that people looked at. Maybe learning rho completely is an overkill. Like why should I want sigma to be close to rho in trace distance? Maybe there is an alternate learning models that one could look at which are kind of more efficient, and maybe that's good enough in practice. So you want to learn only certain aspects of rho. You don't want to learn rho well enough. And this motivates me to this notion of PAC learning quantum states. PAC stands for probably approximately correct. We looked at this yesterday and day before. But I think yesterday and day before when we looked at it, we kind of looked at learning Boolean functions in the PAC setting, but now I'll be talking of learning quantum states in the PAC setting. Right, so we looked at tomography so far, and one way to view tomography is the following. Like, so for example, I gave you copies of rho. Your job is to output a sigma such that sigma and rho are close in trace distance. And if you just write out the trace distance, what does that mean? That means that for every E that you pick, which has operator norm at most one, trace of E rho and trace of E sigma are close. So for any E of your choice, trace of E rho and E sigma are different. That's the output sigma that you should have produced me. But let's just relax this goal a little bit. Let's just say if I want to learn rho approximately well, by which I mean for most E's, I want to learn, so I want the output sigma to satisfy that trace of E rho and trace of E sigma are close for most E's, not for every single E. This kind of seems like a simpler task. And this kind of motivates the model of PAC learning. Yeah, so like Scott Aronson introduced this model in 2003, and kind of the motivation was classical PAC learning, where classical PAC learning has been this rich area of study from 1984, and it's like kind of like the go-to learning model for which you would like to say, I can learn in the PAC framework, which is theoretically very interesting, although in more recent times, like I don't think PAC says much, but it's theoretically nice to know. So Aronson was motivated by the classical PAC model, and he introduced the quantum PAC model in the following sense. Right, so Leslie Valiant had introduced in 1984. So the learning model is as follows. I'll first give the pictorial view, then I'll give you like the details. So QA is still the quantum algorithm. Instead of being given copies of rho now, it's just going to be given uniformly random E1 and trace of rho E1, E2, trace of rho E2, and so on and so forth, and given like EK and trace of rho EK. It's going to be given several different such things, and needs to output a hypothesis sigma such that sigma and rho are close to one another. Let me be a little bit more clear. So think of D, it's a distribution on all possible two outcome measurements. So it's a map from script E to the 0, 1, it's a distribution. And the learning algorithm obtains E1 to EK sample from this distribution D. So somebody samples E1 from this distribution D, E2 from this distribution D, so on and so forth, EK from this distribution D. And along with E1 to EK, they also provide trace of rho E1 to trace of rho EK. Recall that rho is the unknown quantity. And the goal is to produce the state sigma, and sigma should be close to rho, but as I hinted in the starting of this slide, I don't want sigma and rho to be close in the trace norm. What I want is for, okay, what I want, okay, this is slightly complicated, but let me just break this down a little bit. Okay, this 1 minus delta is what makes back learning different from tomography. For most two outcome measurements, sampled from this distribution, for now think of D to be just uniform, that's totally fine. For most two outcome measurements, I want trace of rho E and trace of sigma E to be closed, to be epsilon closed. If I pick delta to be 0, that's kind of in the framework of pack learning. For every E, trace of rho E and trace of sigma E are closed. That's what trace norm actually means. But if I want it for most E's, that's kind of what pack learning is doing. This is clear, like fundamentally, like that's why like pack learning is like a weaker notion of tomography. Yeah.
Are there any non-trivial bounds on how bad can the trace distance be given this condition satisfied? Can it be arbitrarily bad?
Yeah, I'm sweeping something a little bit under the rug here. The point is the distribution comes in here. So you could always pick a bad distribution for which you're only doing well under a
But I
certain.
suppose it's uniform somehow?
I'm sorry?
If the distribution is one observable.
Sure.
It's quite easy.
But
I suppose it's uniform.
uniform distribution, I guess that's fine, right? You could pick like a constant fraction of E's for which you're doing a horrible job, but for still like 3/4 of the fraction, you're still doing a good job. For 1/4, you're doing a bad job. In which case, the trace distance will always be bad, even if one thing is bad. Even for like everything except one if you're.
Exactly, it's arbitrarily bad.
Yeah, exactly.
I think just like concentration of the hard measure, if you just pick like a random state, you'll be close with almost like with large probability.
Right. So that's
all the traces are going to be close to 0. But like they're going to be really small.
That's true. So that's why this is like a much weaker notion. Exactly. Yes. Good. Again, so I'd like to emphasize that this delta is what makes tomography different from pack learning. So this is a much weaker task. And yeah, I've just recalled the entire goal here. A rho is unknown. I keep giving you EI, comma trace of rho EI. Produce a state sigma such that this is closed for most E's that you could have picked. And okay, the basic question that Scott looked at was, okay, the complexity of tomography is D square, and it's optimal as well. You cannot do anything better. D is to the n, so that's bad. Okay, pack learning kind of weakens the goal, but can you maybe hope for a saving? Maybe does it become D? Does it become like root D? What can you hope for? And surprisingly, what he showed is the sample complexity of pack learning is just log D. So we can exponentially improve the complexity of tomography if I allow this weaker notion. And the slightly different learning model, you can get an exponential saving. Yeah.
Is this like with respect to all possible distributions or only with respect to the uniform?
All distributions. Yeah. For any distribution that you pick, I could have always just taken log D samples and done well under that. And I'll try to give you a simple proof case because primarily although this is everything quantum, like there are only two things that are quantum here. Everything's a purely classical result. So there's nothing really quantum going on here. Okay, what's the idea? So the idea is you take log D many samples. So D is this unknown distribution. You just take K to be log D, just get E1 to E log D, trace of rho E1 to trace of rho E log D. Get these many samples. You get this from a quantum device. You go back to your lab. You just try to find a sigma that is consistent with what you just observed. By which I mean, go back to your lab, try to find a sigma such that trace of sigma EI and trace of rho EI were close on all these EIs. The log D many EIs that you just saw. And that's it. That's all the quantum algorithm is. And of course, the natural question is, why does this work? Like, that's it. Like, the entire quantum part is already got done in bullet 1. Like, the question now remains in the analysis, like, why does this simple algorithm? You can think of it as like a greedy algorithm. I just saw a few things, and I just find something that fit all the data that I just saw. Why does this work? And kind of answer goes back to like classical classical learning theory, where you kind of look at, there is this notion of VC dimension, which kind of characterizes how many examples that you need to learn function classes. So this is what VC theory tells you. So the idea is the following. So think of f rho as a function. For every row, I can associate a function f subscript rho that maps all e's to 0, 1, defined as f rho of e is just being trace of rho times e. So it's just a bounded function between 0 and 1. And think of a concept class. Like this is what like yesterday, Matthias, Ryan, and there were some more talks talking on pack learning, where they kind of looked at concept classes where there are functions that map e to maybe Boolean, maybe to bounded values. So think of this as my concept class. For every unknown quantum state row, I have this f rho that maps e to 0 to the interval 0 and 1. And one thing that we know is, this is again coming from classical learning theory. Like, for example, if you want to learn an unknown concept class rho, it suffices to just take something called the fact scattering dimension So if you just take fat shattering dimension copies of this many example states, that suffices to learn rho. I'm not going to define fat shattering dimension, but you can think of this as just a combinatorial dimension that has nothing to do with quantum or anything. If I just give you a bunch of functions, there is this combinatorial parameter I can associate to this truth table of these bunch of functions, and that's it. Yeah. So you can think of, I give you a bunch of functions, write down its entire truth table. I just stare at this truth table. I get a combinatorial dimension out. It's called the fat shattering dimension. And surprisingly, just this combinatorial dimension tells you exactly what is the learning sample complexity. All this hard work has already been done by classical learning theory. What Scott just observed was if rho is an unknown quantum state, I can always find this concept class, one for every quantum state rho, f rho, and then I just essentially like, this model is essentially what you would do for learning real value functions in classical learning theory, which people have analyzed, and they've shown that the sample complexity of learning is exactly the fat shattering dimension. Yep.
I think I've never appreciated actually the significance of these results, because it really doesn't really mean that if you know how a quantum state can be observed in a logarithmic number of measurements, you know actually what happens to any other measurement as well, on, you know, with the pack kind of restriction. So basically, I know somewhere there has to be simplicity in the world that I'm surprised about.
I guess the point is somehow like, let me get to it in 1 second. Okay, let me get to it in a second. So, okay, we said that fat shattering dimension captures the complexity of learning all quantum states. And we know that this is just too surprising to be true. And like, for example, it could just have been that fat shattering dimension of this concept class, which consists of all possible quantum states, could have just been large. But this is where I think something Scott proved a very fundamental result. He showed that the fat shattering dimension of this concept class, and see, this concept class is kind of infinite, you might say, one for every quantum state. He showed that the fat shattering dimension was actually just log of the dimension of the concept class. It was order n. Yeah, so I'll get to you guys. So the point is somehow, although this is true and it's very, it's kind of very fundamental, there are many interesting concept classes for which where this dimension is just exponential in n. So it's not like very often that you see that the VC dimension of fat shattering dimension being small. It's just a combinatorial dimension that captures learning. It could have just been large, but it so happened that coincidentally for this interesting class of quantums, for this class of functions that Scott looked at, it was actually polylog in D, or just log D.
Made many restrictions about their class. Right?
No, we have made no restriction about the class. So it so happens that, yeah, that's true. Yes.
Just want to follow up. If you have two arbitrary distribution, and by taking a log D samples, can you distinguish them? You can't, right?
I mean, if they're actually arbitrary, maybe they could just differ on one point, for which I would think it's hard. But if you're promised that these distributions are far in the first place, then log D, I think, should suffice. Yes.
Oh, I was going to ask, so find a sigma that's consistent. I'm just curious, but you mean like within epsilon or something?
Yeah. Like find a sigma that is epsilon close to all these E1 to E log D that you obtained.
Okay, and also, yeah. Okay.
This could be hard, like.
It's NP hard, right? Almost for sure. It's not even in NP, right?
You can formulate it as STP.
Yeah, you can formulate it.
Large.
It depends on polynomial in D. Like you could do it in polynomial D, right? Just go through all possible.
Right, so it's exponentially hard in NP.
Yeah, that's true.
It's not even in NP, right? Because the witness might be exponential large. So.
But also the E's take exponential time to read anyway. So
Yeah. In a way, like, yeah.
You have succinct descriptions.
Okay. Yeah, succinct descriptions, it might not be hard anymore. Yeah, that's a good question. Is it? Do you know?
I think you can put in SAT, hide inside in the measurement or something, no?
Okay. I mean, worst case scenario, you can write this as an SDP, trying to find a sigma, and this SDP runs in time polynomial in D, 2 to the n. So that's what you can do for sure. Sure, it's exponential time. And to answer everything, yeah, there are some examples where the EIs could be succinctly described, like, I don't know if Daniel's going to talk about it, but for example, like even just to learn stabilizer states, you can think of EIs just being like Clifford poly observables, in which case you can do it in polynomial time, but these are like special cases.
There are cases where it is NP-hard, but it just depends on what
Right.
you mean. What
Exactly.
kind of distinct state, succinct state you're talking about.
Yep.
I think this relates to what you just said. Can you remind me what the EIs are? Are they
sample from some POVM? Can it be just like any operator? What are the EIs?
Just think of D as the distribution on all possible two outcome measurements, or just like all possible operators with operator norm at most one, say. E's are just sampled from that distribution. For simplicity, you can just think of it as uniform on, say, polys, for example. That's an easy way to think about it. Yeah.
Sorry. Can you explain what is random access code?
Okay. So random access code is this thing that, for example, give me a sec. Think of it this way, like forget quantum states. Let's just think of X as an n-bit string. What is the minimum? And let's just say there are two parties. So I have X. You don't know anything about X. Let's just say I can send you a message, a classical message, and somebody gives you an I. Your goal is to tell me your goal is to output what is Xi. And random access code is like a way to kind of encode my X in a message such that you could, for every I that you're given, you can output Xi. And people know that people have good bounds on random access codes. It's random access because kind of randomly for any I that you have in choice, you can access my X. So that's why it's random access. And people know bounds on the communication length here. And you can port everything to quantum states as well. Like I can have a quantum state, you can have an observable. How well can you obtain trace of rho times E? And people know good bounds on the quantum communication, classical communication. Yeah.
So there will be a corresponding result in classical distributions, right? For example, if rho is just a diagonal matrix.
Oh yeah, definitely.
So was it known before this? Or?
Oh, I don't think anybody looked at it, but classical distribution, people have looked at this a lot, like just classical bounded functions. Like this entire concept of fat shattering dimension was motivated by classical learning theory people, like back in '88 itself, people knew this. I'm sorry. Oh. Yeah.
So do I have any control over what EIs I get the expectation values?
Good. That motivates me to the next part of the talk. Here you don't. That's pack learning. Unfortunately, that's a drawback of pack learning. You don't have access to what EIs you get. Oh yeah, okay. I mean, I think I've driven this point enough that the sample complexity of pack learning is exponentially better than tomography, but the time complexity is still large because you need to do the first bullet, which takes exponential indeed time. So although it seems like it's exponentially better, it's just in sample complexity, it's not in time complexity. Good, that motivates me to the next part. Like somebody said, for example, this concept of shadow tomography. So far kind of what we looked at was we kind of estimated rho on a distribution of measurements.
So the time complexity is entirely classical?
I think you can just write it classically, yeah, that's fine, yeah, it's just optimize over D by D matrices that satisfy, that are PSD and trace one.
After you sample these log D samples, you obtain these log D samples, you're done.
Yes. There's no more quantum anymore, exactly.
But the problem itself should be QMA complete because it's like the marginal reconstruction.
But you're doing it approximately. In marginal reconstruction, you want to do it like exactly. Here, you're happy if you do it for most E. So I think that's where this.
But once you have the samples, I mean, so if you have log in samples to reconstruct sigma, isn't that QMA complete? Because it could be that you got the marginals of you could think of them as
I don't think so. Like I think you can just write an SDP for it.
Yeah, but the SDP runs an exponential.
Sure.
From answers, so it could still be QMS.
You're right. Whenever somebody says you can write an SDP, I'm like, that's easy. But you're right. It's easy in exponential in D. Yeah, sure. Good. So the point is somehow we just learned rho in pack learning on a distribution of measurements. But let's just say I want to learn rho only on a certain set of fixed measurements. So let's just say, again, you have this quantum algorithm. It again obtains copies of rho tensor T. But I also know that I only care what is the trace expectation value of rho on this fixed set of E1 to Ek. So somebody tells me ahead of time, okay, on this E1 to Ek, tell me what is the expectation values of rho. So you need to output a sigma such that trace of EI rho is close to EI sigma, but only on this E1 to Ek. Remember, in tomography, it had to be for every E1 to Ek. In pack learning, it had to be for most E1 to Ek. Here in shadow tomography, it has to be for this fixed E1 to Ek that I give you. This is specified by the algorithm itself. I'm sorry?
I mean, just think K would be enough, right?
Oh yeah, I'll mention that. So just to be clear, so E1 to Ek is specified to the problem. The question is how many copies of rho suffice to estimate trace of rho E1 to trace of rho Ek. So there are two trivial algorithms for this. One is you just do tomography, because if you learn rho up to trace distance epsilon, that means you're close for every E, in particular this E1 to EK. And the complexity of tomography is d squared if you allow entangled measurements. So that is one trivial algorithm. There's another trivial algorithm, like what Vedran was saying. You can kind of just say like, okay, I take 1 over epsilon squared copies of rho and just measure it with respect to E1. So E1 comma identity minus E1. I just measure 1 over epsilon squared copies, and I just see how many of them are accepting, and that kind of tells me what is the value of trace of rho EI. So this is for EI, and I do this for E1 to EK, and the complexity is k over epsilon squared. So this is the empirical sampling algorithm that takes k over epsilon squared copies. Tomography takes d squared copies. And the question is, can you do better? So what Aronson observed in like 2017 is he says you can use ideas from online learning and packed learning. And he said that you can estimate all these trace of rho E1 to trace of rho EK by making a giant entangled measurement on these rows. So nothing what I'm saying is works for separable measurements. If you make a giant entangled measurements on rho, I can estimate all trace of rho E1 to trace of rho EK using just poly log K and poly log D many copies of rho. So this is like exponentially better than, it's exponentially better than naive tomography or this empirical sampling algorithm. So that's the beauty of shadow tomography. And this has like, I think you might know already, there are several like follow-up works kind of improving the dependence, trying to see follow-ups, maybe looking at interesting E1 to EKs, interesting classes of quantum states, time complexity, so on and so forth. But the surprising thing is if I fix E1 to EK, it just suffices to get poly log or poly log k many samples, and the dependence on n is just polynomial in little n or poly log in d. I'm just going to give you a quick summary of the protocol, but not too much in details. But is the framework of shadow tomography clear?
Maybe it's a stupid question. What if I take sort of a covering of all possible measurements, which are, it's going to be like 4 to the n of them, and then I get log of that there, which is going to be n, then I recover the first result?
Okay. So okay, good. That's a good point. So the dependence here is, if I'm not wrong, log square d. If you use the same algorithm for tomography, I think you're going to get a d cube or a d4 algorithm. If you can improve the shadow tomography algorithm to just log d, you could have exactly recovered the tomography algorithm. Yeah, that's right. So that's an interesting open question, like getting the optimal dependence for shadow tomography. Yeah.
So what's the cost of doing one measurement, like trace of rho E1?
One copy of, 1 over epsilon square copies of rho.
But when we actually do this trace, so how do we actually calculate it? Like, do you do the summation of like psi, h psi, something like that?
No, I just take rho, I measure it in, think of the measurement E1 comma identity minus E1. I just measure rho in this 2 outcome measurement, and I get like a yes or no. I repeat this thing 1 over epsilon square many times, and I take the average of the number of yeses and nos I get. That would be a epsilon approximate to trace of rho EI. Okay. Good. So let me kind of just touch upon what the protocol here is, but not too much in detail. Right. The problem is, this is a shadow tomography problem. So the kind of protocol idea involves 2 main things. One is this idea from communication complexity that Scott had like very much back in the day. So he had this idea of communication, idea and communication complexity in 2007, which kind of solved a similar problem, but not completely. So think of it this way. So there are 2 parties, Alice and Bob. Alice has a quantum state rho. Alice knows everything about E1 to EK. But Bob doesn't know rho, and Bob knows only E1 to EK. The goal of Bob is to output trace of rho EI. So think of, I'm Alice, I have rho. You have E1 to EK. I know everything. So I know everything. I know my quantum state rho. I know E1 to EK as well. But you don't know what is a quantum state that I have in my hand. I know it explicitly in hand. And your goal is to output trace of rho EI for all the E1 to EK that you have in your hand. And the idea is kind of like, what does Alice do in this protocol? She kind of says like, okay, fine. Initially, you know nothing about rho. She just says, okay, let's just say you start with this assumption that rho is the maximally mixed state, because that's the best assumption that you can start with. So there's this idea of kind of like online learning where she I kind of help you. I kind of tell you, okay, look, on E1, you're doing a bad job if you start with the assumption that rho was the maximally mixed state. So I tell you, okay, on I, you're doing a bad job. I tell you what's I, and I'll tell you what a trace of EI rho. So the point is somehow on this EI, the trace expectation value of what you should have thought it should be and what you should have thought it should be and what it actually is far away, is delta far away. I will tell you, okay, on this E1, your delta far away, trace of rho E1 and trace of sigma E1 are delta far away. So look at E1 and correct your quantum state, update your quantum state. So you start with a quantum state sigma 0, which is maximally mixed. You update it to sigma 1, where sigma 1 kind of updates the fact that you know on E1 I did a bad job. And so this is like a communication problem that Scott looked at. And Scott showed that it suffices to just send polylog D and polylog K many bits of communication for Bob to finally output all these trace of rho EIs. Again, this was back in maybe 2006 or 7 already. And Scott kind of looked at this because it was just a cute communication problem. But if you already look at it, this already kind of smells like shadow tomography. There are a few differences, which I'll talk about now, but kind of this already looks like shadow tomography in a way. So what's the main difference between this communication problem and shadow tomography is just that first things first, there is no Alice. There is no Alice, there's a Bob, he knows E1 to EK, and he just gets copies of this quantum state rho. So that is a shadow tomography. There's no Alice, you get copies of quantum state. Your goal is still the same, using these copies of this quantum state, output trace of rho EI. So what it's, the first observation in the shadow tomography algorithm on top of this communication complexity was this idea of quantum OR lemma. What the quantum OR lemma says is the following. Actually, let me just write it this way. So think of, I give you copies of rho. There is E1 to EK. The quantum OR lemma takes log K. It's just like polylog K many copies of rho and tells me, is there one J for which EJ times rho is large, or for every J, EJ times rho is small? So the idea is kind of like, I have E1 to EK in my mind. I get copies of rho. This quantum OR lemma tells me if there is one J for which trace of EJ rho is large, or for everything trace of EJ rho is small. And surprisingly, you can actually do it in polylog K many copies. So this was again developed by Scott in an earlier paper, but it was improved and things like that by follow-up papers. But this is one crucial ingredient. And you can think of this quantum OR lemma as kind of the step 2 here. Like kind of telling me whether trace of EI rho is far away from trace of EI sigma. And that's kind of what Scott simulates here in this quantum OR lemma. So that's the first thing. The second idea that goes in is kind of the quantum OR lemma doesn't tell you what is J. So remember, this is just this, but Alice kind of helps him and helps Bob by telling what is the I on which I'm doing a bad job. All the quantum OR lemma is telling there is an I for which I'm doing a bad job. It doesn't tell me what is the I on which I'm doing a bad job. Again, here Alice was there to send me that, but in shadow tomography there is no Alice. And for this, what Scott does is he just does like some version of a binary search. Just take E1 to EK over 2, EK over 2 plus 1 to EK, kind of find if there's a bad J here or in this bucket or this bucket. Based on that, you just do a binary search, and you eventually can find the J. And that's it. So you have simulated the work of Alice in step 2 by just using the quantum OR lemma and this binary search.
Right, why does step 2 suffice in step 2 in the above protocol? Because like, there's also a sigma I.
Right, yeah, that's what I'm hiding a little bit. There is a little bit more work here coming in. So kind of you should think of this, maybe I'm overloading notation. You think of rho as being rho minus sigma in step 2 there. So essentially what is this? This is trace of EI times rho minus sigma I. So you should think of, let's just rename this thing. Okay, this rho here should have been rho minus sigma I here in the step 2 there.
I think you're given log K copies of rho and not rho minus sigma I. So how do you do this?
Right, the point is sigma I is known to Bob explicitly on his own. So he can simulate the fact that you have sigma I explicitly. So that is also an interesting thing here. The point is like Bob, he has a sigma naught to begin with. He updates it to sigma 1, sigma 2, and so on and so forth. The fact that he knows sigma 1 to sigma 2 is what Alice uses a lot. Because you could have asked the same question here, how does Alice know, what is the state Bob updating his state to? The fact that she knows it here is what is crucially used here. And the fact that Bob knows sigma 1, sigma naught, sigma 1, how he's updating the quantum state is actually used crucially again in the quantum OR lemma.
Get a question from the outside. Obviously we're only looking at sample complexity, not time complexity. I kind of get that.
Correct.
Because, so very often we make assumptions that we kind of can have a state, you know. And I always thought that this type of stuff was super useful for applications, but this seems to be completely not the case, right? So in the lab, really, I want to know what a state is, then I'm much more interested in a classically efficient description of the state, and I try to approximate that one, or the best one I can in a certain family of states. classically described. I don't know if it's even a question.
This might just be nomenclature. What's called shadow tomography and the classical shadows protocols are completely different.
Exactly. So I'm not going to touch on classical shadows, but there was this follow-up work of classical shadows. That is something people are actually, like Robert has a sequence of work.
But still, so in general, so this is more than an academic question. I'm more thinking about, does this help me now to really learn something in a lab? Or is this more...
I would think so, coming from a theory perspective, but I think this should be useful.
I'm
But
not criticizing, I'm just trying to understand,
no. So the point is, in a way, what I think in a way what you're saying is correct. So the point is, I think, there was a follow-up paper of Robert Preskill and Robert, where they kind of improved shadow tomography to classical shadows, and that has actually been done in the lab. Like they have a lot of these works in Nature and Science where they actually kind of experimentally do stuff with it. I'm not super familiar with it, but there is some follow-up works that do some experimental implementation of classical shadows. But for me, this is just academic interest, but I believe what you're saying. Like, this seems super interesting.
It's totally fine.
The time complexity is very porous.
Yeah, sure.
I think
like
in
a first
practice
step.
also the main issue might be that you need to like do entangled measurements.
Correct.
Across many copies of rho. But classical shadows, I think the advantage is that you can just do one copy at a time.
Exactly. So that's an advantage of the. So this, that's a major drawback of this. One is the time complexity is bad. The second is you need to perform giant entangled measurement on low tensor-T, whereas the classical shadows just perform single copy measurements, and you can still do a version of, maybe the version of shadow tomography. Yeah.
But what if we have more than one J, which satisfy that?
The point. If there is one, as long as there is one, that's good enough.
Okay, it is more than one, it's okay?
It's totally fine. Yeah. Exactly.
You can determine all J's?
Again, by the binary search, you should be able to. Yes. Yeah, so there have been few works trying to improve the dependence on this, and the state-of-the-art work is by Costin Barasco and Ryan O'Donnell, where they have log square k, log d, and epsilon to the -4. Good. I think I'm done with part of my talk. So far, what did we see? We saw tomography, pattern learning, and shadow tomography. These are, I think, very interesting results. But as I said, there are several works in this direction, which I don't have time to cover. There's this work of classical shadows. There's a work of online learning. Then people have looked at shadow tomography for k outcome observables instead of 2 outcome observables. We do have lower bounds on shadow tomography and standard tomography if we only allow separable measurements. And then there's learning quantum channels and quantum processes. Maybe Robert might talk about it. And then people have looked at tomography for interesting class of quantum state, like matrix product states, states produced by low-depth circuits, time-dependent quantum states, Hamiltonians, and so on. I'll be touching about a couple of these things in the second part of the talk, but there are several results that I haven't covered yet.
Can you remind me, if you go back, like if you take k to the exponential in n, like why doesn't this contradict the bounds of shadow, like of the normal tomography?
If you take k to be 2 to the n, you should.
Because of the epsilon.
Yeah,
Exactly.
Can you explain that? Like it's because of the epsilon, right? Yeah, but
Epsilon has to go as 1 over 2 power n if you wanted to reconstruct the entire state.
Okay, thank you.
So you'll get a d to the 4 upper bound, which is, and like going back to what Vedran was saying, if you want the d square upper bound, you need to improve the epsilon dependence.
Will you say more about the channel version? I mean, of course, that is immediately narrated by like looking at the choice states and so on. But that's kind of the poor man's version for the channels. There must be also an interesting version. Will you say more about this?
I don't think I'll talk about it. Like I know Robert is talking about quantum processes, so I think he might touch upon it, but in like 2 talks from now. But I'm not going to touch upon it. No, I think after Daniel's talk.
Okay.
So Daniel's talking next, and Robert is talking after that. So he might touch on quantum processes learning, quantum channel learning. Good. Yeah, there's several works, and I'm not touching upon that. But let me talk about a couple of things which I think are interesting. One is this learning classes of quantum states. So kind of, so far we saw like if you want to do doing tomography on an arbitrary quantum state, the sample complexity was exponential, the time complexity was exponential, which is not great, but maybe can we restrict our attention to interesting classes of quantum states and still hope for a polynomial sample or polynomial time algorithm? So one such thing that we worked on a few years back was this Hamiltonian learning problem. So the idea is you're given copies of a Gibbs state of a Hamiltonian. The goal is to learn the Hamiltonian. So think of H to be a k-local Hamiltonian, geometrically local, acting on n qubits for simplicity. You can always write H in terms of the Pauli decomposition. Just think of EI as the 4 to the n Paulis, and each have this coefficient mu i's. This was similar to the setup I think somebody spoke about yesterday or day before, where they have this operator write it in the Pauli basis. The only thing about H that you don't know is the fact that these mu i's are unknown. That's it. You're given copies of the Gibbs state, e to the minus beta h, where beta is the inverse temperature, and trace of e to the minus beta h is the partition function. You're given copies of this quantum state rho. Your goal is to unlearn these unknown mu i's up to L2 error epsilon. You can look at other norms as well, but for simplicity, I'm looking at L2 norm epsilon. So this is a problem of learning a Hamiltonian given copies of a Gibbs state.
So, what does this imply in terms of the error on the operator? Is this implying epsilon error on the operator? Induced distance between h and h prime?
If you have an L2 error being small, then the operator norm is fine. But if you have an L infinity error, you might need epsilon to be much smaller for the operator norm to be smaller. Yeah, so the motivation for this problem is there are a few things. One is the way I got into this problem is there's this bunch of classical works. I think Patrick spoke about a bunch of works of Clivans and Goyle. Classical people learn these graphical models, and we just wanted to do quantum graphical models. What's this thing? Okay, it seems more natural quantumly than classically, but classically there's been a lot of attraction on learning graphical models given copies from the Gibbs state. So that was my motivation, but then when you write a paper, you kind of say there's a physics motivation for it because the Gibbs state is like the steady state quantum state of a Hamiltonian at a temperature beta, and then maybe if you have to prepare the Gibbs states of a local Hamiltonian, if you want to verify it, doing verification is same as learning, or maybe a harder task, but learning is one way to do verification. So there is much more motivation, but I think it's just a very natural problem. And the main result that we had a few years back was what we showed is the sample complexity of learning, of outputting a mu prime that is close to mu, where mu's are the unknown coefficients here, is polynomial in little n. Forget all these other exponential things, it's just polynomial in little n. So remember, tomography complexity was exponential in little n, but we can show that when you look at this interesting class of quantum state, the sample complexity of learning is polynomial in little n. It requires entangled measurements and things like that, but yeah, at least the sample complexity can be exponentially reduced for this interesting class of quantum states. I'll give a brief proof sketch of this. Yeah, so when we looked at this problem in the first place, I'm just recalling the problem here. Rho mu is the unknown thing. You're given copies of this Gibbs state, and H is the Pauli decomposition here. So when we looked at it first, the first thing you do is just apply shadow tomography. You know all these E1 to E4 to the n because it's a Pauli decomposition. They're 4 to the n Paulis. So do the 4 to the for each one of these Paulis and try to estimate what is trace of EI rho mu, and you can do that by shadow tomography in just polynomial in little n many copies of the quantum state. So this is nice. And the question is, once you obtain these EIs or EI primes, can you recover mu? Recall, the goal is to recover mu I, not to just recover EIs. And yeah, to approximate this, you could have just used either Scott's shadow tomography protocol or the follow-up works of HKP and CW. And the question is, okay, fine, like you obtain the EI, you obtain E1 to E4 to the n primes that kind of approximated these EIs, but is this good enough to produce a rho prime? You can go back to the lab, try to find a rho prime that's consistent with all these EI primes, and you can produce a rho prime. The question is, this rho prime that you produce need not even be a Gibbs state. It could have just been an arbitrary quantum state. So it's not even clear why rho prime that has like the same sufficient statistics as rho mu is a Gibbs state. It could have just been an arbitrary quantum state that just has like the same statistics. So the first observation that we had is, okay, fine, maybe you don't need to optimize over all quantum states, just optimize over all Gibbs states. Just find the Gibbs state for unknown betas. Oh, sure, sorry, there's a typo, it should be in beta. Oh, no, actually it's correct. So just maximize over all Gibbs states where the H has its coefficients lambda i's, and try to find the best Gibbs state that approximates your EI primes that you obtained by shadow tomography. And the first observation is, if supposing we had exactly EIs but not EI primes, then the quantum state that actually satisfied like rho lambda, trace of rho lambda EI and trace of rho mu EI was exactly the actual unknown Gibbs state. So if we had this, if epsilon was 0, if I exactly had E1 to E4 to the n, I went back to my lab, found another Gibbs state that had exactly matching expectation values that would have been my unknown Gibbs state. So that's nice, but unfortunately we don't have these little EIs, we have only little EI primes. And the question is isn't this hard? So there's this idea of kind of maximum entropy principle, or the Jaynes principle that people have used a lot in even quantum semi-definite programming. You can cast this entire problem as an optimization problem, as a semi-definite program or a cone program. So what do? Try to find a sigma that is PSD and trace 1 such that trace of sigma EI is equal to little EI. And the sigma that maximizes this entropy thing is actually this unknown Gibbs state. So what is the idea? Okay, let me go a little bit slower. So I run this optimization problem. You can think of it as an SDP for now. Find a sigma, or that is what you're optimizing over, PSD trace 1, such that trace of sigma I is equal to little EI, where little EI is exactly this. And find the sigma that maximizes the entropy. And it so happens that you can show with a little bit of work that this maximum is actually equal to the unknown Gibbs state. Yeah. Right. I think you can relax it to a second order cone program. Yeah, I think you can do it. Yes, exactly. Like, I don't know how to do it, but like optimization people are saying you can reduce it to a cone program. There's some quantum work on this as well. Good. So yeah, so if you solve this program, you would actually find the unknown Gibbs state. But there is an issue as always. The issue is kind of like you're not solving this optimization problem, you're solving this optimization problem. Because these EI primes given to you by shadow tomography are only approximations of EI. You don't exactly know EIs. And the question is, okay, fine, maybe knowing the approximations, is that good enough? Maybe. And that's not the case actually. The point is if you know only just approximation EI primes that are close to EIs, you can show that the sigma that you get here and the sigma prime that you get here and the sigma that you get here will be very far away from one another. And the reason for that is the following kind of, like, okay, what are these EIs? You can just think of it as taking the log of this Gibbs Gibbs state. And when you take the log of this, you're going to get mu here and mu prime here. But when you take the log and they're very close on the x-axis, which is what shadow tomography is promising, on the y-axis it could be extremely far away from one another. So just by obtaining approximations here and solving this approximate problem is not good enough to get a good approximate of the unknown Gibbs state. So this is the basic issue. I'm running through the slides now because I want to finish in 5 minutes, but good. So the main thing that we observed is kind of like, okay, this is our algorithm actually. It's actually purely in a way, the only first step is quantum, everything else is classical. So get copies of the Gibbs state, do shadow tomography and estimate all the EI primes that are close to EI rho mu. What we do is in the previous slide, I spoke about the primal optimization problem. You can look at the dual optimization problem. That is just this, that's not too hard to see. But unfortunately, you don't have little EIs, you have only little EI primes. And the question is, how close is mu from mu prime? Recall the goal is the output approximation of mu. And this is where the hard work comes in showing that these two optimization problems are actually nice. By nice, I mean that you need to show the strong convexity of the quantum partition function, which we were able to show in our work. That's the most technical part of the work. And once you show that the quantum partition function is strongly convex, you can actually show mu and mu prime is actually close to one another. And yeah, let me make a few remarks before I'm done with this application. First is our algorithm is not at all time efficient because to solve this optimization problem could take exponential time because you have to evaluate the gradients of the partition function, which is not easy. But the nice thing is it kind of just takes copies of the Gibbs state and just does like all the hard work is done in step 2, which is kind of classical, but the quantum part is just step 1 where you're just doing shadow tomography. You just obtain like expectation values and you're kind of done. So it's kind of classical, but along with quantum expectation values. The complexity depends exponentially in beta and kappa. This seems bad, but we know it generally can't be avoided. You cannot hope for it to be polynomial in every parameter. It has to be exponential in beta or kappa by some classical results. And yeah, so the main thing is there was after our work, there was this work of Ha, Kothari, and Yuan Tang, where they kind of showed how to make our algorithm polynomial time, but only in the high temperature regime. But there was this breakthrough work last week by Bakshi, Liu, Moitra, and Yuan Tang, where they get polynomial time algorithm even in the low temperature regime. So they completely kind of resolve this problem of learning Gibbs states, learning the Hamiltonian from given the copies of the Gibbs states in complete polynomial time. Okay.
But the latest one is still exponential and beta.
Yes, it's exponential.
That's a
Double exponential.
Is it doubly exponential? Oh, I didn't know that. Okay, so that's unavoidable.
Just a very quick scientific question. The mu is normalized, vector mu is normalized somehow.
Yes.
So you cannot put in exponential many bits in few copies, right?
Yeah. Good. So the two things I wanted to talk about, thankfully, other people are going to talk about it. The first thing is learning stabilizer states. So one annoying thing about everything I spoke about so far is all sample efficient, but not time efficient. But Daniel is going to talk a little bit about learning stabilizer states. These are one of the few quantum states that we know how to learn time efficiently. Yeah, I'll wrap up. And so yeah, Daniel is going to talk a lot about this. He's going to learn. In fact, his talk is not just going to talk about states that can be learned just prepared by Clifford circuits, but also log n T gates, which I think is a very interesting development in the last year. Yeah, I'm not going to talk about this at all. Learning phase states. We had this subsequent work. Good. So the final thing maybe I'll touch upon before I go to some open directions is this quantum statistical query, which I'm kind of excited about. I think this is a very nice line of research, which we are kind of looking at now, is kind of like, so just think of a concept class as a bunch of quantum states. So as Brian was mentioning in his talk, you can either perform a giant entangle measurement on all copies of this quantum state. That's nice, but that's not really experimentally feasible. Like, this just seems hard. You can maybe ask okay, I perform only single copy measurements. I get a copy of rho. I perform a single copy measurement. I keep doing this. Can I still learn the unknown quantum state? So that's a weaker model. So there's this QSQ model, or the quantum statistical query model. You'll hear a lot about tomorrow. But I'll just try to tell you how we got motivated to define this model in the first place. So even entangled and separable measurements are maybe far away from near term. But I suspect that the statistical query model is slightly more near term, in the sense okay, what's this model? All that you have to do in this model is you have to specify an operator m and precision level tau, and it kind of gives you a tau approximation of trace of m times rho. So rho is your unknown quantum state. You give the algorithm m and tau. It just tells you what is a tau approximation of trace of m times rho. That's it. So QSQ algorithm is at IBM we can prepare a quantum state. You being a classical learner, you can just tell me an operator and tau, and I will tell you what is the tau approximation of trace of m times rho. So this is quantum statistical query. We define this motivated again by classical statistical query. And the question is how many QStat queries are necessary and sufficient to learn the unknown rho. Yeah, the idea somehow in the cloud possesses a quantum state. The learning algorithm is purely classical. Maybe it's a client. He wants to learn properties about this unknown quantum state. You can view such a practical application of quantum computing in this theoretical framework maybe. That's kind of what we motivated us to define this model a few years back. And one thing we observed in the paper is kind of every learning algorithm that we have actually can be embedded in the statistical framework. So that kind of was surprising to us. So kind of we asked this question a few years back, is there any problem for which statistical queries are much harder than even entangled queries? Yeah, so we answered this thing in the negative, that is statistical queries are far weaker for even even for stabilizer states. And I think Vojta and Louis are going to talk a lot about it tomorrow. Yeah, I think that's it. Yeah, and this kind of strengthens a few works that we saw yesterday from on learning from the Born distribution. Good, yeah. So let me just conclude quickly. I think this is a rich area of study. There's a lot of work left to be done. For learning structured unitaries and structured channels, there is some work left to be done. Agnostic learning, I think somebody touched upon it yesterday. I think Matthias's work touched upon it yesterday. We still don't have answers to fundamental questions. What more quantum states can be learned time efficiently? I think the more the states that we can learn time efficiently, the better. We have only a few examples right now. There is also a fascinating connection between sample complexity of learning and the hidden subgroup problem, simulation, communication complexity, and so on. So kind of you can twist you don't need to think of it like quantum machine learning. You can just think of classical problem of your choice. You can kind of take it into the framework of sample complexity or time complexity. There's some unpublished work on learning trivial states, which I've seen a talk about, learning low-rank stabilizer states, that's still open. And the question is, from a theory perspective, I would like to know how implementable are these algorithms. I don't think so, but it would be nice to understand how implementable they are with experimental noise. With that, I thank you.